In a number of videos on my YouTube channel, I have discussed the performance of various adsorbents like Shabasite, C3H8 cast 7, magnesium MOF 74 for separation of propylene from propane with the objective of producing a polymer grade propylene. The adsorbents that I've just mentioned are all selective to propene and therefore can only be recovered in the final vacuum blowdown step. Life is much simpler if we use propane selective metal organic frameworks for separation of propylene-propane mixtures. Today, I consider two such adsorbents, nickel ADC TED 0.5 and CAO3 BDC, discussed respectively in the two papers listed here. In the paper by C3H8, that is from South Korea, the following graph compares the uptake of propane and on the y-axis with propane-propene selectivity, and the two adsorbents, CAO3 BDC is shown here with a selectivity of about 1.3, and nickel ADC TED 0.5 has a selectivity of about 6.3. Let's re-examine the performance of these two MOFs, and I'd like to make a few remarks on how these two MOFs should be compared. The first point I'd like to make when comparing propane selective MOFs is that the comparisons should be based on the separation potential that is calculable from the IAST. The separation potential is described in my ACS Omega paper 2020, and the expression for the separation potential is delta Q is equal to Q1, the component loading of species 1, which is propane in the mixture, calculable from IAST. Q2 is the component loading for component 2, which is propene, and Y20 and Y10 are respectively the mole fractions in the feed mixture of component 2, propene, and component 1, propane. So for a 50-50 mixture, this ratio is unity, and for a mixture of propane to propene in the ratio of 1 to 15, this factor here, Y20 divided by Y10, is 15 divided by 1. The physical significance of the separation potential is that it represents the maximum productivity of purified propylene that can be recovered in the adsorption cycle of a fixed bed adsorber. If we do the calculations for a 1:15 mixture of propane and propene, the values of the separation potential and propane selectivities are shown here for CAO3 BDC and nickel ADC TED 0.5. It is clear that nickel ADC TED 0.5 has a significantly higher separation potential, and we should therefore expect a significantly higher productivity of purified propylene in the fixed bed adsorber. Let's see if the breakthrough experiments and breakthrough calculations support this prediction. The experimental breakthroughs for the two MOFs, nickel ADC TED 0.5 and COW3 BDC, are shown here. The breakthrough experiments for this MOF was conducted for a 50-50 mixture, and for COW3 BDC, the experiments were conducted for a 1:15 mixture of propane to propylene at two different flow rates, flow rate of 5 milliliters per minute and a flow rate of 3 milliliters per minute. The first point to note is that the time axis here is in minutes, and here it's minutes per gram. In several earlier presentations on my YouTube channel and also in my ACS Omega paper published in 2020, I have made a plea for presenting breakthrough experimental data using the modified time parameter shown here, the flow rate in milliliters per minute times the time in minute divided by the gram of MOF in the packed tube, and this x-axis the units of milliliters per gram or liters per kilogram. If indeed the experiments for COW3 BDC for these two different flow rates had been plotted with this modified time parameter, we would have been in a position to check the consistency of these two breakthrough experiments, because with this Q0T divided by M adsorbent as the modified time parameter, the two breakthrough experiments would or should have collapsed into a unique curve. Almost, there may be small differences due to diffusional influences. In any case, on the basis of these two breakthrough experiments, it's not an easy job to compare the performance of propylene-propane separations based on these breakthroughs. So let's see how meaningful comparisons can be carried out. For a like-for-like comparison of the two MOFs, they should resort to transient breakthrough simulations carried out under identical conditions. So let's perform the breakthrough simulations, and for COW3 BDC, and for that purpose we need to examine the unary isotherms. In the paper by Chitale published in Chemical Physics Letters 2023, the unary isotherm data have been fitted with this dual site Langmuir-Freundlich parameter with temperature dependent parameters K1 and K2. What is strikingly odd in my way of thinking is that their calculations as presented in this paper of the isostatic heats of adsorption are not based on the dual site Langmuir fits with T-dependent parameters, but rather on the virial fits of the unary isotherms. And the calculated values of the isosteric heats of adsorption using their virial fits are shown here. What would have been much more elegant and more accurate would have been to use the dual site Langmuir-Freundlich parameters with temperature dependent K parameters to carry out the calculations of the isostatic heats of absorption, because the Clausius-Clapeyron equation can be used with analytical determination of these derivatives. I have discussed this in several earlier video presentations on my YouTube channel. If I do that, I see that the isostatic heats of absorption of propane and propylene are practically identical, and the values are rather different from those determined from the virial flits. I'll leave it to the authors of this paper from South Korea to ponder over whether it is indeed meaningful to recalculate the heats of absorption by using their DSLF fits, which they have already used to determine the IAST selectivities. I proceed with these isotherm fits to determine the transient breakthroughs in beds packed with Cow3 BDC. The transient breakthrough simulation strategy is described in my earlier paper published in ACS Omega, and taking due account of diffusional influences, I calculated the transient breakthroughs for 115 mixtures of propane-propylene for a flow rate of 3 milliliters per minute, and these are the breakthrough simulations that are in good agreement with the experimental breakthroughs reported in this paper by Chitale. So the first step in my procedure is to validate the breakthrough simulation methodology, and the breakthrough simulation methodology is found to be of good accuracy and may be used for comparing the separation performances of the two different MOFs. The transient breakthrough simulations for 115 mixtures of propane-propylene in Cow3 BDC and nickel ADC TED 0.5 are shown here, and I use the modified time parameter Q0T divided by the mass of adsorbent as x-axis with the units of liters per kilogram. It is clear, even visually, that there is a significantly larger gap between the breakthroughs of propane and propene, and this would result in a significantly higher productivity of purified propylene using nickel ADC TED 0.5. The overall message that emerges from this video is that for comparison of MOFs for separation of propylene-propane mixtures that are selective to propane, firstly, we should use IST calculation of the separation potential, delta Q, as I mentioned earlier. And if experimental data are available and are measured, please use the modified time axis parameter as shown here. This will allow comparison of different MOFs much more easily. In any event, we may perform transient breakthrough simulations to compare the separation performances of two different MOFs by conducting these simulations at identical conditions. In this case, the conditions chosen are 3 milliliters per minute as the flow rate of the inlet feed mixture.